But one of the key things that makes this crazy, there's two reasons why you would believe something so crazy. First is two independent competing teams got the same result. And then once you've put that into your model of the universe, you then calculate a new age for the universe that turns out to be a bit older than we thought. And that solves what was up till then a really embarrassing problem. If you look at in our galaxy, the oldest stars in our own galaxy, the Milky Way, this is quite close to us now, they're in big lumps of about 1 million stars called globular star clusters. These globular clusters are the oldest things we can see in the galaxy, and we can measure the age of those stars. It's about 13 billion years old. 10 years ago, our model of the universe embarrassingly said the universe was younger than that, maybe, I don't know, 11 billion years old. That's embarrassing that we had calculated the age of the universe, but we could see right next door to us these objects that were older than we thought the whole universe was. Something didn't add up. Once you've got this observation that the universe is speeding up, you then calculate the age and it becomes older, old enough to contain those nearby globular clusters. So we're beginning to believe that, yes, this is the right explanation. There's something else in the universe. The way it works is currently completely unknown. There's two options. One is that there's some mysterious stuff that we don't understand, we can't predict, but no idea that's actually pushing galaxies apart. And we call that dark energy, just for want of anything else, because we haven't got a clue what it is. The other alternative is that there's something fundamentally wrong with the law of gravity, with as described by Einstein in general relativity. And that would be pretty worrying. It would mean we have to completely rewrite something in the physics textbooks. Some of the laws of physics are wrong. We've got two options, we don't know what they are, and this is such a fundamental issue for physics that we use to model the world, the universe, and indeed the history of the universe, that it's been rated as one of the top 10 science questions in physics and astrophysics for this century. It's so fundamental that we might be rewriting the laws of physics when we find the explanation for what's going on.
That's pretty fundamental stuff indeed, and I guess it comes as a great surprise to many astronomers and physicists. So I guess that explains the problem. So what's the method for tackling it as far as WiggleZ is concerned?
Okay, I'll use this opportunity to explain the strange name for our project. The thing we're going to do is test the idea that the dark energy has had a constant effect over the last 10 billion years or so. One of the popular models is that it's what's Einstein referred to as the cosmological constant, which has a constant effect like a pressure pushing things apart. And what we're going to do is look at the spacings between galaxies about 10 million light years away back in time, and see how that's been affected, how the light, as it travels from those distant galaxies to us, is affected by this expansion getting faster. The trick we're going to do is, when we look at the distribution of galaxies, we're going to use the fact that there's a pattern on very large scales in the distribution of all matter in the universe that was imprinted on the universe right in the earlier stages about 300,000 years after the Big Bang. So if we look back in time, in the early universe, there was a very faint pattern in the distribution of matter, and that has been seen in the microwave background radiation coming from the Big Bang. Coming forward, this pattern is still there in galaxies. It's a very faint pattern, but it has a fixed length. And what we're going to do is we're going to go back, look at the galaxies about 10 billion light years away, and pick up this pattern. And when we draw our graphs, that pattern will appear as a wiggle superimposed on the smooth distribution of galaxies. So we'll be looking for the wiggle in our graphs. Now, what we're doing here at the telescope is we we're starting with a list of galaxies, and we have to measure the distance as indicated by something we call redshift, which is like a Doppler shift in the light from each galaxy. And astronomers use the letter Z as a shorthand for redshift for this thing we're measuring. So we're looking for the wiggles, and with this wonderful telescope and the instruments behind me, we're going to measure the redshift, which is the Z. So WiggleZ is the name coined for the survey, and it's not a coincidence that several members of the team have young children who watch Australian television.
Right. And in terms of, and that's clear. And in terms of instrumentation, how do you propose to actually gather this information?
Okay, here's the wonderful Australian technology side of the story. Back 10, 15 years ago, if you were trying to measure the redshift indicating the distance to a galaxy, you'd get a big telescope, like the one behind me, and you point it at one galaxy and feed the light from the focus of the telescope into a spectrograph to split it up into its different colors and look for features that have been shifted from their normal wavelengths by the redshift of the galaxy. And then you measure the shift, and that tells you its redshift, which indicates how far away it is. We need at least 250,000 galaxies for our measurement, and we'd never be able to do that one at a time. And to solve that problem, in comes the Anglo-Australian Observatory with their wonderful technology using optical fibers. So instead of taking the light from one galaxy at a time at the focus of the telescope behind me, what they do is at the focus they position 400 optical fibers, which will take the light from each of 400 different galaxies all at the same time. So the focus is quite big, so we can focus many objects together, but traditionally we only got one of them into the spectrograph. We actually use 400 optical fibers positioned across the focus to collect the light from 400 galaxies. That's done in the black thing up the top of the telescope behind me. And then the 400 optical fibers go down the side of the telescope onto the floor of the dome, where there's a large spectrograph that can process and analyze that light to make 400 spectra of each of the galaxies, which we can then measure. So now in 1 hour we can do 400 galaxies rather than just one, and in something like 200 nights on the telescope we can collect our 250,000 measurements. The big thing to point out here is that Australia is really invented this technology and is leading the way, so that when it became clear that this was the next experiment to do, this was the only facility already running in the world ready to start the experiment. So we have about a 4-year lead on the rest of the world in doing this experiment.
Cool. And how long did it actually take to build such a beast?
It's the end result of probably 15 years of technology development through previous instruments. There's two components that are both very complicated, but the real challenge is up the top of the telescope. Those 400 optical fibers have to be moved into different positions every time you go to a new patch of sky, because the galaxies are not distributed in the same places. You've got to design the positions for that particular patch of sky according to your list of galaxies. And up the top of the telescope, there is a robot that picks up each of those fibers one after the other and moves them to the new place. It does that incredibly accurately and very quickly. It only takes an hour to take the 400 positions from the last observation and move them to a new position. And there's actually 2 sets of fibers, so while it's setting up the next one, it's got one looking at the telescope actually being observed. That's incredibly complex technology, and as I said, Australia is leading the world in that. We now export this to other observatories internationally. That's the hardest bit of it.